I know a lot of you didn't have her for A. And so she might integrate this as you move along. I like to, as you can tell, pretty much open every workshop with a spectra problem. Sometimes IR, sometimes H, sometimes carbon. I have this figure. This is posted on Canvas. This is workshop 4. And so carbon's actually way more simple than hydrogen. So here are your ranges to look for when you have a carbonyl. Really, these are the ranges you should be looking for. Essentially, from 0 to 70, sp3 carbon, no problem. The 80 to 100 is where you'll see sp, and then 100 to 150 is where you'll see sp2 carbon. So way simpler. You don't need to worry about counting neighbors. You don't have that information here. All right. There is a decoupled NMR where they do try to get that more complex. Most of the ones you will see will be straight. Here is decoupling, meaning just telling you the types of carbons. Okay. And I will say that there's a big hint in the hydrogen NMR, which you all talked about in A, to what type of structure you have here. Okay, so I'll give you a couple more minutes. And this will be posted on Canvas. You'll have access to this figure if she hasn't shown it to you. But I'll give you a couple more minutes, and then I'll do a little introduction, and we can get started.
Question.
Yeah.
Will you only post this figure here, or the whole slide?
So I will post that figure on the key for workshop 4. Okay, so for example, just to give you guys an idea, this is what I would have done for workshop 4. And I'll talk more about that in a second, but this is essentially what was workshop 4, and the keys either have been published or will be published by the end of today if you want to try and go back and do extra problems for stuff you talked about last week. But so I will post that figure. Okay. I'll go back because obviously it's a little easier to see from the slides. But just to give you an idea, I will post pretty much everything I think that's valuable. Not every single word, but everything I think is valuable will be on the key to the worksheet after I do it that day. Okay. Anyone sneak in that didn't have a handout? Okay, it's 11:10. So again, if you just came in, my name is Dr. Brandon Bogus. I am doing the workshops here for Summer 2 for 118B. It's been a while. I last did these workshops, I want to say winter 17. I've mostly been working with the 8 series content, so it'll be a little bit, not new, but it's been a while since I taught these. If you've been working with Edna, I do things very differently from her. I really try to make this more of a workshop, meaning you are encouraged to write down things from the board that I've sort of left as a treasure map for you in the worksheet I've given you. That is not everything that you need to write down today. You are filling in the gaps, writing things where you need to, working on problems, working together with students on problems. All right, so I do expect you to come here not thinking this is a lecture. I will be walking around in probably a couple minutes to see how you're doing with this spectra problem. So I know where you are, and I can try to meet you from there. I don't have a website, have a separate Canvas shell. These are all the workshops that I think I would have done last week if I was here, probably a little bit faster. So even though it's the 4th day of workshops, we're on workshop 5 just because spectra, depending on the professor each quarter or summer session, I know I try to go as fast as I can to keep in mind with that. After you're added to this, I will have to manually add anybody who hasn't signed up for it at the end of workshop today. After you're added, I will always have the whole week's workshops, what we're doing, essentially 5 Tuesday, 6 Wednesday, 7 Thursday, so you know, hey, do I want to come to workshop today? What is Brandon talking about? Okay? I did last week. These are already the keys that are up, meaning after we do a workshop today, I will post the key, meaning all the fill-in questions we may not get to, depending on how time works out. On the home page, I have additional hours. This office hours, I know you're in class, but I also offer support for the 8 series, and they are not in class at that point, so I like to have some time beforehand. Mondays are my general office hours, and then 2 to 4 Monday through Thursday, either in my office or in the drop-in room for any additional questions. Okay, so that's up on Canvas. You don't need to write that down. If you want to take a picture of it, it will be up on the SASC website later today, and it's also outside my door. Okay? Any general questions about workshops? I do not post any slides. Excuse me. I don't post any slides because I really want you to leave with a one sheet. Here's everything Brennan talked about today. But I do expect you to try to follow along. You're not just looking at the key afterwards. The more energy you put into this workshop, the more valuable I think it will be for you. Okay. So I'll give you another minute. I'd like to see how everyone's doing with this first Spectra question, so I can maybe fill in the gaps with hydrogen NMR, or potentially talk more about carbon. I'll put this back up. I will tell you here that your ranges that are important are going to be is 200. That should be a hint for you. So I will tell you that in your carbon NMR, the one on the right, if you look at your x-axis, right, that's the big difference. Right, we never saw anything 50 to 100, right? Hydrogen was always like 0 to 10, maybe 12, depending if there's a carboxylic acid. So I'll say that here the ones that are important are we're looking in our 100 to 150 range, and we have a carbonyl based on that 200. Okay? So I do have a more zoomed in picture if you're curious about it. It's a little tough to put together when you see hydrogens that far downfield, but I do have it. So you have your integration. Remember, carbon does not have integration on it, but if you wanted to see what those would look like, there are the zoomed in pieces of them. When we see hydrogen signals that are messy in the 7 to 8 region, what type of hydrogens are we thinking about? These are very common. You'll see this signal a lot. And it's okay if you guys are not sure. I would imagine in this room there are some people who took A last quarter. There are some people who took A while ago. So different professors. So I can't say for certain everyone knows this. Anyone have an idea? Between 7 and 8 for hydrogen NMR? Aromatic hydrogens. Okay. I see some nodding, so some people remember that. I like to ask questions like that. I'll be waiting longer until I get answers if I need to. Silence it makes you guys talk a little bit more. But I really want this to be more of a modified discussion than a lecture. I know you go to lecture all for 2 hours, you want to take a break and then come to another hour. I don't think that's great. Right? So I will be asking you either turning to your partner, talking to me, giving me some answers. Let's have a discussion about what you guys are learning. Okay? So it's okay. Today's the first day. If you haven't talked about Spectra that much, we'll keep doing a little bit as we go along. I know there's already a Spectra problem for tomorrow. And so just want to see where everyone's at. If you don't have any work, you're not sure, that's totally fine. But if I'm saying aromatic, I should see something of a starting point. Think about I'm only really seeing 4 types of hydrogens, and my huge peak that's upfield is a singlet for 3 H's. What functional group would we be saying that is going to represent? Any ideas? If I see a 3 hydrogen signal, got to be a methyl group. Does it have any neighbors? No, right? It's a singlet. So think about, well, how is that going to be used on a benzene ring? If I have 5 unique hydrogens that are in my 7 to 8 range, how many bonds are on my aromatic ring? How many groups are on the outside of that, right? So I'm saying I'm seeing that I have my 5 hydrogens on downfield. I'm starting with this. I know I have 5, meaning one of these positions has to have a group on it. If I say I just want a methyl, let's see if that would work. I still have my 5. These would be the same, right? We could say these are HAs, these are HBs. This would be HC. There would be my top one. But what's the problem if this was my answer? How many carbons have I drawn here? 7, right? How many do I have in the formula?
8.
8, and I also know that this guy tells me carbonyl. One more. So here's C, here's my new HD, there's my carbonyl. I got 8 carbons, 8 hydrogens, my oxygen. That's the answer.
Just a quick question.
Yeah.
Did you not have a C bond O on one of the carbons and then a methyl on the others?
So then I wouldn't have an extra hydrogen here.
Oh, okay.
That's the problem. And I will tell you that, if having a di-substituted ring, whether the relationship is next door or on the middle position or on the opposite position, that really changes the NMR a lot. And so when you're trying these practice ones or exam ones, think about that. Because I actually think it's going to be really hard for you as second semester or second quarter students to tell the difference between this and whether that methyl group is here or here, right? You'll have a little bit of difference with these hydrogens, but in some structures it actually will be really difficult to tell. Okay? So I will always give you the actual signal so you can tell where those groups are. We would be able to tell that the one here on the opposite position was our single hydrogen, and then we had A's and B's next door and in the middle. I'll also give you the carbon one with the actual signals in case you want to know that. And so I will post these on the key with the individual signals if you want to follow back with that. Anyone come in and knock in a handout too? Okay. So can you pass those back for me? Great. Okay. So, like I said, I'll try to, just in case the students get here early, I know you're coming from class, you're probably not going on campus, I'll always have sort of a warm-up problem. Maybe it'll be spectra, maybe it will be something we talked about in the previous workshop. Usually students are most concerned about spectra, so I try to do most of those to start out with. I hope by the end of this quarter, if you're continuing to see or not, spectra will get a lot easier for you. Okay? Carbon NMR really helps a lot. And you don't have to worry about memorizing all those IR spectral bands and stuff like that. Just those simple regions. Okay? So, let's start with our reactions. So what you've talked about last week was this concept of Markov-Nikov addition. Markov-Nikov addition is telling me that I am adding my nucleophile at the more substituted carbon or the less substituted carbon. More substituted, right? Anti-Markov-Nikov, right away, I'm going to be adding my nucleophile to the less substituted position. And so this is one of the cool things. I actually didn't learn this until late in my second semester. And it's for synthesis, this helps a lot. Right? If you've ever seen any of these problems where, wait a second, you've always had pretty much secondary and tertiary groups, because those are the ones you know how to make before. Now we have a totally opposite situation where I can add a group to the opposite position in the double bond. So the first reaction here, we're saying less substituted carbon. We're going to be talking about hydroboration, oxidation. First step is going to be using boron, THF for a solvent, and you actually can get this commercially available, so that's why you'll see that solvent paired up with that. That's going to make this tri-substituted boron compound, and notice here, our goal is to turn that piece to where our nucleophile is going to add, right? Boron is just sort of a placeholder in this reaction. And so the mechanism's kind of long here because we need to be able to get to here and then get to here, get rid of the boron, trade spots. But in general, I think it's a little easier to spot because if you have a predicting products question, this really is going to be maybe one of two reactions where you'll see boron. So if you see boron, that is your indicator. I'm thinking anti-Markov-Nikov here. All right? So how do we get this part started? And as I have on your sheet there, I might start your structure from something I put on the board so you're not writing everything, but I don't want to include all the arrows. So that first step, I have that structure written for you, right? That's where I want you to start filling in from there. So hydroboration, what we've already talked about with electrophilic addition, right? What we now have as an additional nucleophile is double bonds. So my double bonds going out and grabbing my boron, just like we saw with traditional Markovnikov addition, just like we saw with the bromonium ion. And the only difference here is we're going to have a transition state. This should look a little bit like the bromonium ion because we had this sort of 3-member transition state. Well, with boron, it's 4. And a couple things here. If you had to redraw this, already, if we're seeing boron, you're thinking anti-Markovnikov. That's where the boron needs to be inside that double bond. Now, it's really actually about a steric argument here, but what I like to think about is an electronic argument. Well, if we think about what we've seen before, we always saw hydrogen being added because it was the most positive element or positive piece in our system. And if we think about the location of where boron is relative to carbon, it's actually less electronegative. Hydrogen, same as carbon. So in that boron-hydrogen bond, hydrogen's more electronegative, meaning boron's going to be partially positive. So I like to remember this as if boron's going to be partially positive, in Markovnikov addition, we have the partially positive atom going to the less substituted position. Same thing happening here. And it's really a Steric's argument, meaning size, how is this nucleophile going to get in there? But that's how I also remember it. Boron's sort of being actually more positive in that. Why is he showing up as negative here? He has 4 bonds, right? So having the overall negative charge versus the charge in a specific covalent bond are 2 different things. So if we had to draw this out, we're going to see the boron being to the less substituted position. And what I like to see here, right, is if one of these carbons is going to have the positive charge, who's going to be the better carbocation? Well, right now my partial positive is on a tertiary position. And if I added it the other way, it would be on a partially positive secondary position. So the rule still applies here. So that we want to have our most electrophilic atom on the less substituted position. It used to be hydrogen, now it's boron. And we want to make our best carbocation. Right? So even though, and I'm very big on being able to see these similarities moving forward. Right? And so being able to say, that's really not that different. It's anti-Markovnikov, but what we did was switch the elements that are in those spots. We really had the nucleophile, the negative nucleophile, adding to the more substituted position in this bond. That's hydrogen. Right? So not really different as the concepts of how we're making that bond, but the atoms have switched. And so what that means is, in this transition state, it's going to break down and will actually turn out breaking that bond. And if we think about how that transition state has to form, that's going to be going in the same direction. So let's talk selectivity with this type of reaction. We can say it's stereoselective because both of those groups have to be going in the same direction, right? Same direction, syn addition. And in addition to that, no matter what I do, it's anti-Markovnikov, so it's also regioselective because my boron's being added to the less substituted position. So I can't get anti and I can't get on the more substituted position. If I wanted my nucleophile, now if you already heard this in class, you know eventually we're turning this into an alcohol. If I wanted an alcohol on a more substituted position, I can do that. I don't need to worry about boron. I don't need to worry about hydrogen peroxide. So 2 key aspects of this. So that is step 1. That is the hydroboration. Oh, sorry. Go ahead.
Could you repeat what you said about the stereoselective and regioselective?
So stereoselective meaning that since this is a cyclic transition state, both of those bonds have to be going in the same direction, right? And so same direction, syn is the way we're describing that. The regioselective, what I care about is always going to be my non-hydrogen atom, meaning my boron group is always going to the less substituted position. If I want my group to be going to the more substituted position, you already know those. That's Markovnikov's rule. right? So this is the way to get around that. How can we get a primary alcohol, right? That's how can we make a primary halide? That's not something you've been able to do. So yes, this mechanism's tricky, it has lots of steps, but this actually opens up a lot of easier doors in your synthesis questions, okay? Because now, once you make primary halides, you know all these wonderful SN2 reactions that can change functional groups in one step. Whereas secondary halides, we have a lot more to worry about. Okay? So I think this is going to make your lives a little bit easier for synthesis questions, and I have some examples at the end that allow us to do that. Everyone okay with that? Wow. And she is very big on this. First thing I did, I got added to your Canvas. I already looked at exam 1. I know it's not till next Thursday. But I'm saying, what is the type? I don't know any series exams. I haven't seen them in a while. And she does have some multiple choice saying, when are species being formed? Which types of reactions are these? So she does like to ask this, being able to tell stereoselective or regioselective. And I also think that I like to know that in a reaction because it helps me draw the mechanism out if I have to. Right? I'm saying, okay, hydroboration, I need to see stereoselectivity and regioselectivity. So as I'm drawing this, okay, well, if it's stereoselectivity, I know that I need to show that my ring, transition state, is going in the same direction. So, stoichiometry-wise, right, boron likes to have 3 bonds, so we actually can use 1 mole of boron for 3 moles of alkene. Meaning the mechanism I just showed you is actually going to happen 3 times, right? We're adding our R group to the boron and essentially replacing each one of those individual hydrogens. So what I have here is replacing it once, replacing it twice, and replacing it 3 times. Okay, this is just from a stoichiometry perspective. At this point, we can go on to step 2, oxidation. And how that's going to work is we have our H2O2 that's essentially going to turn into an ion. Remember, we also will have base here. And so we will see my hydroperoxide coming in as a nucleophile. And I don't have my R groups written here, but we're effectively at the end of that last piece. So I have my R groups coming in here, my hydroperoxide. Now, this arrow should be fine. Sort of reminds me a little bit of SN2, nucleophile coming in. This one's something new. We haven't really seen an arrow like this before. And the reason why is you haven't talked much about peroxide bonds. OO single bonds are very reactive. But if you can think about where we've drawn something like this, what does this remind you of? Any ideas? I think it reminds me of a couple different things. I'd say one could be, yeah? I think perfect, a rearrangement. I think that reminds you. So you're looking at this and saying, whoa, those arrows are tricky. Where have I seen something like this before? I think I could say rearrangement. One other thing. I'm having, rather than coming to this atom, we've seen this before with elimination. If we draw this arrow to the bond and kick that out, that's an elimination mechanism, right? So trying to see these, hey, this is not completely new, but I think this is the hardest arrow in the entire mechanism. And I will say the driving force for this is this weak OO bond. What can I do to get rid of that? Right? Why is it so weak? Well, we got 4 lone pairs there. 4 lone pairs, these electrons trying to potentially be electronegative atoms, right? So they want to steal electrons, and now oxygen's bonded to another oxygen. They're both fighting that they're the same strength in a tug of war. So I would say combination of those 2 things there. So we end up making OH minus, not a great leaving group, but this is under basic conditions, so it's okay. And all we've done by that arrow is replace my OH group with my R group. What's the other incentive here? Why else is this picture problematic? And it's staring you right in the face. What's the other incentive for this to get fixed here? We said when we started, boron likes to have how many bonds? 3. How many does he have in that picture? 4. That's another problem, right? So I'm looking at this and I'm saying, okay, don't really have anything else this can do, right? We have no basic hydrogens here. So if we can't be a base, we're going to be a nucleophile. At that point, 4 bonds, well, I have to break one of them. If my peroxide group leaves, that just brings me right back to where I was. Right? So I'm very big at trying to be able to say, hey, what can you possibly do? Right? You've had a quarter of OChem, whether it was recently or not. You should have the general basics. Okay, well, how could I draw some arrows? Even if you don't know how to name what you're drawing, you should be able to tell me what are some things we possibly can do. And then we're going to narrow that down each chapter. So our alkyl groups moving over, replacing that OO bond, turning into effectively almost like an ether, but with a BOR bond instead of a COR bond. Okay? First reaction, we used 1 boron, added our alkyl group 3 times. Same thing here. I need to have this happen 2 more times, where my peroxide would come in, and just like last time, this R group is then moving over to the other side of that oxygen bond. And now I like to say at this point, right, really the arrows after this should make sense. If we are oxidizing a bond, I'm adding a new oxygen carbon bond, right? And so why this part's important, the entire goal of all of this is to make an alcohol. Here's my O, that's going to be my alcohol. So our last step, oh, and so this is just shorthand. This is simplified what I'll have at the end of that process, right? Boron with 3 groups that are all OR groups. So at the end of that process, right, we're saying here's what we have left. We have hydroxide already in there. This would be the same arrows. Hydroxide coming in, kicking out our OR group. My OR group is then going to become my alcohol. So if you think about this step, we just did that arrow with the peroxide. Still, if you're saying, well, what else could happen here? I'm adding hydroxide, still have no acidic hydrogens because all they're going to be that are all the hydrogens that are there are going to be CH hydrogens. So here, nucleophile adds, boron has 4 bonds, something needs to leave. I got 3 groups of the same thing. If my OH leaves, I'm back to where we started. So a lot of similarities here, and I think this is probably one of the tougher mechanisms in the chapter 12, but a lot of similarities with what we've seen before, rearrangements or elimination, whichever one looked like it was easier for you to remember. And then here, same as the last one, our peroxide came in as a nucleophile. Rather than shift anything, if we shift this R group, we're just going to turn it into the same thing. So now I'll have my OR group. Here is my alcohol. Notice now that that OH is on the end of my R chain, meaning it's a primary alcohol. So all of this whole thing is about how can I make my nucleophile add to that outside position, the less substitute. So our OH minus is going to act as your nucleophile. You usually have water. That hydrogen from the water is the alcohol hydrogen, right? Because we're kicking out our OR minus, meaning that needs to steal a hydrogen. Why water? Well, we want already have sodium hydroxide, so by taking the proton off of water, we've made more hydroxide during that process. So a lot of work, but if you see these are the easiest ones to predict, right? Because you're going to be seeing your H2O2. Think of what we've used water before. Essentially, you're going to have a double bond. And now my OH is going to be on the less substituted position rather than the more substituted position. Right? And so if you really know Markovnikov's rule, then this is the exception to that. You see boron, I'm adding my nucleophile to the less substituted side. So what I'd like you to do is take a minute, just refresh, go ahead and look through that whole mechanism now. Make sure you're okay. Because there are pieces that are confusing. And as you're doing that, try doing the bottom 2 questions. haven't attended a workshop with us before, this is our sign-in tablet. I'm going to ask you to select Dutton Hall, the 118B workshop, and then add your student ID number and hit submit. Okay. This is just like any other device. If the Wi-Fi drops, you can hit the Wi-Fi symbol, and then I only have 2 bookmarks there, the same thing. To me, the trickiest part is making that association between boron and anti-Markovnikov. All right, and we're going to add one more exception when we get to free radicals that really, if you see a peroxide, that's going to identify it as anti-Markovnikov too.
Question?
Yeah.
For that second part where it was oxidation with the hydrogen peroxide,
Yeah.
could the hydroxide ion compete with the hydrogen peroxide ion to attack the boron?
So at this point, we're saying that there probably wouldn't be any more peroxide around. Right? That's from step 2.
Right.
I'm going to say that you're right, there might be competition, but at this point, that peroxide broke apart to create hydroxide, which is what we needed as a next reaction for this next step. Right? So each time we're adding that peroxide piece, we're generating hydroxide as a result. So for these two, these should feel pretty simple, straightforward, right? This first one, nothing's changing except I'm getting rid of my double bond. I see that my nucleophile is hydrogen peroxide. That tells me I have an alcohol. So hopefully you're getting pretty good at these. If this was Markovnikov addition, you'd make a secondary alcohol. Here we see boron. We're thinking primary, less substituted position. Now I like this one because how am I going to show this position becoming sp3? Does it matter? Remember how this whole thing gets started. My hydrogen and my boron group need to be going in the same direction. So if that matters, you need to show me that. Right? So I need to see that there's syn addition between this OH and H. As to whether or not they're coming from the bottom or the top of that ring, you'll talk more about this starting next week, maybe a little bit on Friday. We actually prefer the outside piece there, exo versus endo. I think there's a document in the file section if you were curious of what that meant. But that's why it's coming on the top of that ring. But I would say as long as you're showing me the OH and the H here are in the same direction, I'd be fine. It really probably is a racemic mixture at that point. Okay. So boron is our way of adding an alcohol to the less substituted position. Something you haven't been able to do until now. All right? Well, what if we wanted to add a halogen? That doesn't help us. Adding hydrogen peroxide is not going to do that. And so what we've seen before with Markovnikov addition of adding a halogen, if I have freshly distilled alkene that hasn't reacted with the atmosphere, I will get my Markovnikov addition great yield, 90%. If I use older alkene, accidentally leave it out on the counter overnight, I can get some anti-Markovnikov addition. And just like we did with boron, if we're seeing anti-Markovnikov, there must be a different mechanism for how this reaction proceeds. Okay? And so what we're going to call this, she also says, I think, the ionic addition of HBr. Here we're going to do the radical mechanism. All right? So HBr can add in both ways. So what happens is that oxygen actually creates a peroxide inside between the 2 carbons in that double bond. So sort of imagine you have an alkene, this oxygen-oxygen bond is going to slide in there. what this ends up happening is now we have our peroxide bond. And you remember from A, you had this initial free radical mechanism. We didn't use it with alkenes. That's the difference here. But our arrows always have to be half arrows here, little fish hooks, because free radical mechanisms, right? Free radicals, they're these lonely little electrons. Each prong on that arrow is represented as a single electron. And so all your arrows in non-free radicals have been two-pronged arrows because we know electrons travel in pairs. Now, free radicals, single electrons. So if you have to reproduce this, make sure you're using fishhook arrows showing that one electron's breaking. And if we look at the result of this, is we have two of the same thing, and we have oxygen having 5 electrons. Not something we've ever seen before. We've always had him having having that negative charge. But this should be a refresher of what you saw in 118A when you were introduced to the free radical mechanism. So at this point, we can continue propagating our radical. So our radical will then add to the radical of an HBr. This is generating an alcohol and our bromine radical. Be careful about adding negative charges to this. In the case of oxygen, he has a single electron to make that bond with my R group, meaning he has a total of 6, which is what he should have. My bromine has a total of 7, that's what he should have. So no negative charges on those, right? So these are going to start our mechanism, and this is going to be faster because once we make these peroxide bonds, they're actually unstable, just as we talked about with our hydroboration mechanism. And so we can't stop this from happening, as opposed to electrophilic addition, our Markovnikov pathway, that really is about what? Markovnikov addition, that speed, that reaction really is how good a carbocation can we make, right? So this, way faster, we have a really unhappy high energetic bond. Propagation steps, we've now added our bromine to an unreactive piece of our alkene. At this point, we've now created a secondary radical. Why is that happening? Just like with carbocations, radicals are going to favor the more substituted position. So kind of neat here. We're using carbon's advantage and what it actually bonds to. And all we're doing is changing either the atom, right? We change hydrogen to boron to make boron go to the less substituted position. Here, we're using a different mechanism to get that bromine on the less substituted position because a secondary radical is going to be more stable than a primary radical. So we still have our radical piece here. Remember, we can either pick up another unradical form of my hydrogen, right? In our last step, we created a hydrogen radical. Or I can react with an unreactive piece of HBr, and then I can continue the chain. So your last step really would be termination, is when you're adding 2 radicals together, but then you're out of radicals. So our propagation step is creating a new Br radical that can then do this part again. Right? And so actually my graduate work was studying with free radical mechanisms, looking at how they affected lipid oxidation. And it's impossible to stop once it gets going because every radical is going to want to react with something else. And so termination is actually the last step and the least common because the likelihood of 2 radicals finding each other is really low. As far as halogens go, these are just some other examples of peroxides you'll see. I think she shows you this diterbutyl one. But bottom line, whether they are showing you what these other groups are or not, if you're seeing a peroxide, that's an indicator that you're using an anti-Markovnikov free radical addition. So these don't happen with chlorine and iodine, but they can happen with other groups. So we will see them with sulfur, following the same arrows we just talked about. My nucleophile is still being added to the primary position. And so here I don't even need to tell you what type of peroxide I'm using. If I have that OO bond, I know that that is an indicator, again, just like with H2O2, that is an indicator for antimercaptan addiction. So some examples of this, right? These predicting products are the easy ones, right? Again, we're seeing HBr. I'm seeing my ROH, some peroxide, don't care which. That means that I'm going to get my bromine on the less substituted position. Bottom one again. Here I'm showing you this piece, right? Don't let that confuse you. That OO bond is right in the center under this arrow. That's your indicator here, that this is not adding via the ionic pathway. It's not adding Markovnikov. It's going free radical, meaning my bromine is not going to the secondary carbon. It is going to the primary one. Any questions on free radical mechanisms? I'd like you to take a minute, just look through our propagation and our initiation steps to make sure you're okay with being able to reproduce those. All our arrows for those need to be single hook. Yeah.
Can I have a look on the propagation step very quick? Thank you.
So internet was being weird again. Dutton Hall, 118B, and your student ID. After you've reviewed that, if you're okay, if you have any questions, what I'd like you to do is go down to the bottom. Some examples of how we can use synthesis or how we can use our reactions we talked about today in synthesis products. And when I assign a problem, it's never individual, right? You feel free to talk to the person next to you. Can you use what we've talked about? I'm not saying everything from today is in here. It's actually a little bit review. But it's just showing how we can use these reactions to our advantage. So since this is my first week with the class, just a reminder, we are Tuesday, Wednesday, Thursdays. As long as we don't exceed the space in here, we'll be in this room. The more people start coming, I'll look into getting a bigger room, but for now, definitely tomorrow and Thursday we'll be in here. New stuff every day. And the workshop sheet for tomorrow is already up. So if you want to say, okay, what are we doing tomorrow in lecture? How does that align with workshop? Hopefully this week, if this is what you talked about today, we should be right on task. I will have 2 more workshops, and then Thursday will mostly be a chapter 12 review too. Okay, to get ready for next week. So if you're taking your notes, I want you to be saying what goes here and here. What is this product? What could I use over this arrow? And what would be my final product here? And again, this is a safe space. I go around to see where you're at. It's not like I'm expecting you to have this totally filled in. I want to know where students are at. Maybe there's a specific arrow that most people are having trouble with. Okay, so do not feel intimidated if I'm looking at your sheet and it's blank. That's why you're here, right? You want to get more practice thinking about how to approach these problems. So don't feel bad about that.
I would say that with alcohol, from A, we would learn something that was better for that.
I would say, right, like think about it, that's an OH. Is there, why is this going to be like that?
Well, I'm just going to say,
Oh, so you have an acid and base? Which
Oh, no, I'll just use water. Like I could.
NaOH with water?
Yeah.
No, I'm saying that wouldn't this rather take the H from the O rather than a carbon?
Oh.
That's what I'm saying. So I'm saying that I like that you're thinking that way, but there's a better way of turning an alcohol into that, and that's not base.
Okay.
Do you have any more extra handout?
I actually ran out. If you want to wait, I will print you another copy right after class. Okay. Yeah, it was the first day. I wasn't sure how many to make, and I hate wasting paper, but I will gladly print you one.
I have mine.
Oh, you're okay? Thank you.
Oh, yeah.
Yeah, so I love if you want to use tablets because it saves paper for me. So if anyone, after today, feel free to, you'll be able to do that. The PDF is already up for tomorrow. You can start writing notes on it if you want.
Is this going to be on our canvas?
This is a separate canvas. So you'll have to, I'll ask anyone who wants to be added to manually add yourselves at the end. Okay? In really 2 minutes.
Oh, I have a question.
Yeah. Yes, that's good. This, well, okay, missing that, but no, that's something will happen there. Yes, that's actually
and then,
perfect.
On the exam, would we have to write out like this, or is it?
I think that'll be okay. I think that's what I've seen you do.
Okay, thank you.
Yeah. That might work. That's not the one I was thinking of. But I see what you're saying. Basically, that step really, if you take a specific acid, that will do that without even having to worry about step 2. Oh, if anyone's not sure of that notation for the second one, that is potassium T-butoxide, right? So it looks like this. That is an identifier for a very specific type of reaction. Does anyone remember from A? When we see this, we are thinking elimination. What type of double bond? More substituted, less substituted? Less, right? It's big and bulky. I'm glad to see this first part. I saw a lot of good answers. I saw H3PO4. That's the one you guys have seen. That's fine. H2SO4. I would say any type of dehydration reaction, you're going to want heat there. And hopefully you were able to see, if my bromine added to that double bond, we wanted to try to use our free radical mechanism to get it there. Okay? So I would say this one was review. I saw H2O4. Anytime we're looking at going alcohol to double bond, those are the reagents that get you there. Remember, we don't need to worry about nucleophilicity here because HSO4 minus is a non-nucleophilic acid. For the second part, because this is a bulky base, notice the solvent here, that is just going to regenerate it. Right? Say this picks off this H. I will get my less substituted double bond. From there, I can use HBr and any peroxide to turn into my bromine at the less substituted position. So again, application of what we saw today. And then here, just a simple SN2 reaction. Okay. So that is everything for me today. And again, what I will have you do, and if you don't want to wait around, feel free, you can just take my email me your UC Davis email. If you don't use it, I'll add you manually to it myself. If you'd like access right now, I'm going to have you come in individually, type in your UC Davis email, then a comma, and you'll have access to this site. Thanks for coming. We'll be doing this again tomorrow at 11:10. That's fine.
Yeah, so this was HCL and HI.
Oh, sorry.